Welcome to Sleepy Space. Tonight, we're exploring one of the biggest questions in astronomy. Just how large can the largest black hole in the universe really become? We'll journey from colossal event horizons to the history of galaxies that built these cosmic giants. Before we begin, please subscribe if you enjoy relaxing space documentaries, and let me know in the comments where you're listening from tonight. Imagine standing somewhere far beyond the orbit of Neptune, watching the solar system shrink into a tiny arrangement of pale lights suspended in an ocean of darkness. The Sun, which feels unimaginably vast from Earth, is now only another bright point surrounded by planets so small they seem almost accidental. Then imagine placing the largest known black hole not somewhere beyond those planets, but directly at the center of this scene. Contrary to what countless illustrations have led people to expect, it would not resemble a giant cosmic vacuum cleaner swallowing everything in sight. There would be no monstrous mouth stretching across the heavens, no wall of darkness racing toward the planets. Instead, there would be something almost unsettling in its silence. Space itself would appear strangely ordinary until you reached a boundary from which nothing, not even light, could ever return. That invisible boundary alone would already be larger than most people imagine possible. And this is where the real question begins. How big is the largest black hole in the universe? The answer is not simply a number. It is a journey into how nature itself measures size, gravity, space, and time. Among the most famous candidates ever discovered is an extraordinary object known as TON 618, an active supermassive black hole whose estimated mass exceeds 60 billion times that of our Sun. Although future observations could refine this estimate or even reveal larger examples, TON 618 remains one of the most massive black holes measured with substantial observational evidence. Numbers this large quickly become meaningless if left on their own. 60 billion suns sounds impressive, but human intuition was never designed to understand billions. Our minds evolved to judge the height of trees, the distance across valleys, the weight of stones in our hands, not objects capable of reshaping the geometry of entire galaxies. To truly understand how large such a black hole is, we must leave behind everyday measurements and enter the language of gravity itself. Unlike a planet, a black hole does not possess a physical surface. There is no solid crust, no ocean, no atmosphere marking where one thing ends and another begins. Instead, its apparent size is defined by the event horizon, the invisible spherical boundary beyond which every possible path through spacetime points inward. Cross that horizon, and according to our best current understanding of general relativity, escape becomes impossible. For a black hole as massive as TON 618, that event horizon is astonishingly large. Its diameter stretches across hundreds of billions of kilometers. Light, traveling at nearly 300,000 kilometers every second, the fastest speed allowed by the laws of physics, would need days simply to cross from one side of the event horizon to the other. Pause for a moment and allow that image to settle. We often think of light as instantaneous because sunlight reaches Earth in just over 8 minutes. Yet here is an object whose darkness is so immense that light itself requires roughly a week merely to travel across the width of the region from which it can never escape. Suddenly, even our solar system begins to feel unexpectedly small. This realization also overturns one of the most common misconceptions about black holes. Many people imagine that as black holes grow larger, they become infinitely dense monsters, crushing everything around them with ever greater violence. Reality is far more subtle and, in many ways, even more astonishing. The gravitational pull you experience depends primarily on your distance from the object's center and its total mass, not on some magical property unique to black holes. If our Sun could somehow be replaced overnight with another object of exactly the same mass, whether it were a neutron star or even a black hole, Earth's orbit would remain remarkably similar. It is only when approaching the event horizon itself that the truly extraordinary consequences of curved spacetime begin to dominate. The largest black holes, therefore, reveal something profound about nature. Their power comes less from violent destruction than from the immense volume of space-time over which gravity quietly dictates the possible futures of everything nearby. Yet another surprise awaits. Larger black holes are not necessarily more dangerous to anything crossing their horizons. Near a relatively small stellar black hole, the difference in gravitational pull between your head and your feet becomes enormous long before reaching the event horizon, producing the famous stretching effect, often nicknamed spaghettification. For a supermassive black hole containing billions of solar masses, that difference across a human body at the horizon can actually be much smaller. In theory, an observer falling towards such a giant might cross the event horizon without immediately noticing anything dramatic at that precise location. The catastrophe lies deeper inside, hidden from the outside universe forever. This strange fact transforms our intuition once again. The biggest black holes possess the gentlest horizons, while hiding the greatest mysteries behind them. It is difficult to imagine a more elegant paradox. The largest prisons in the universe may have the least dramatic entrances, but where could something so enormous possibly come from? The universe is approximately 13.8 billion years old. That sounds like an eternity, yet even cosmic time imposes limits. Building a black hole tens of billions of times heavier than the Sun requires extraordinary conditions. Astronomers believe such giants likely began as much smaller black holes formed during the deaths of massive stars, or perhaps through other processes that are still actively debated. Over hundreds of millions and billions of years, they consumed enormous quantities of gas, merged with other black holes as galaxies collided, and grew alongside the galaxies that surrounded them. Rather than existing separately from their cosmic neighborhoods, these objects appear deeply connected to the evolution of entire galaxies. Every collision between galaxies may have delivered new stars, fresh clouds of hydrogen, and eventually another central black hole, allowing an already gigantic object to become even larger. Yet this picture remains incomplete. Recent observations by powerful telescopes, including the James Webb Space Telescope, have revealed unexpectedly massive black holes existing surprisingly early in cosmic history. Some appeared when the universe was less than 1 billion years old. Their existence has prompted lively scientific discussion because standard growth models sometimes struggle to explain how such enormous masses could have accumulated so quickly. Perhaps the earliest black holes formed from unusually massive gas clouds collapsing directly without first becoming stars. Perhaps growth occurred more efficiently than previously estimated under special environmental conditions. Or perhaps entirely new physical processes remain hidden within the earliest chapters of cosmic evolution. None of these possibilities has yet achieved universal acceptance, making this one of the most exciting frontiers in modern astrophysics. The largest black holes, therefore, do something remarkable. They refuse to serve merely as records in a cosmic competition over size. Instead, they expose the limits of our understanding. Every time astronomers discover another exceptionally massive black hole, they are not simply adding another entry to a catalogue. They are testing Einstein's theory of gravity under extreme conditions, refining models of galaxy formation, challenging assumptions about the early universe, and asking whether our current picture remains complete. Even the darkness itself becomes a source of information. Ironically, we rarely observe these black holes directly. Left alone, a black hole emits almost no light. The reason we know about objects like TON 618 is because the material spiraling toward them becomes unimaginably hot before crossing the event horizon. Gas collides with gas at enormous speeds, heating to millions of degrees and producing brilliant radiation across the electromagnetic spectrum. The black hole remains invisible, while the universe illuminates its surroundings like a spotlight, revealing an unseen actor on a stage. In that sense, we have learned to study darkness by watching light struggle against it. Perhaps that is why the largest black holes inspire such lasting fascination. They stand at the intersection of the visible and the invisible, where mathematics predicts realities that human senses could never discover alone. They are not merely oversized versions of smaller black holes. They represent a different scale of existence altogether, where distances are measured in light days, masses in tens of billions of suns, and the familiar geometry of everyday life quietly gives way to the deeper architecture of space-time itself. And as immense as TON 618 appears today, one final question remains waiting beyond the edge of everything we have measured so far. Is this truly the largest black hole the universe has ever created? Or is it simply the largest one that humanity has been fortunate enough to find before the light of countless other giants has finally reached our telescopes? If someone were to ask how large Mount Everest is, the answer would seem effortless. We measure its height from sea level. Ask how wide the Pacific Ocean is, and we simply trace the distance between two shores. But the moment we ask how large the biggest black hole in the universe is, every instinct built from everyday experience quietly stops working. A black hole has no mountain peak, no coastline, no visible surface that separates itself from the rest of space. It is not a solid sphere floating through the cosmos like a planet or a star. In fact, one of the most fascinating aspects of black holes is that the object itself refuses to offer us a clear edge. Before astronomers can even begin comparing one black hole to another, they must first answer a more fundamental question that sounds surprisingly philosophical. What exactly does it mean for a black hole to be big? That question has shaped decades of research, because depending on which definition we choose, the answer changes in subtle but important ways. There are three different languages that astronomers commonly use when describing the size of a black hole. One speaks in terms of mass, another speaks in terms of diameter, more precisely the diameter of the event horizon, and a third, made famous by the first image ever captured of a black hole, speaks about something called the shadow. At first glance, these may seem like different ways of describing the same object, but each one reveals a completely different layer of physical reality. Understanding why they are different is the key to understanding why the largest known black holes are so extraordinary. Surprisingly, astronomers almost never begin with diameter. They begin with mass. This may seem backwards until we remember that gravity is the defining feature of a black hole. A black hole cannot be touched directly, but its gravity announces its presence everywhere around it. Nearby stars orbit faster than expected. Clouds of gas accelerate to astonishing speeds. Entire disks of glowing plasma circle an invisible center with remarkable precision. By carefully measuring these motions and applying the laws of gravity, astronomers can estimate how much mass must be hidden within a very small region of space. Long before we know how wide a black hole might be, we often know how heavy it is. This is one of the elegant habits of astronomy itself. We rarely weigh celestial objects on a scale. Instead, we let gravity perform the measurement for us. That is why nearly every record-breaking black hole is introduced first by its mass rather than its diameter. When scientists describe TON 618 as containing more than 60 billion solar masses, they are not simply announcing an impressive statistic. They are describing the very property that determines almost everything else. According to Einstein's theory of general relativity, mass tells spacetime how to curve, and curved spacetime tells matter and light how to move. Once the mass is known, something remarkable follows almost automatically. The radius of the event horizon increases in direct proportion. Double the mass, and the Schwarzschild radius doubles as well. Triple the mass, and the horizon grows 3 times larger. This relationship is one of the rare moments in astrophysics where extraordinary complexity gives way to beautiful simplicity. Yet even here, language can quietly mislead us. The event horizon is often described as the surface of a black hole, but that picture is only partly correct. It is not a physical shell floating in space. No wall suddenly appears. No material boundary exists that could be touched by an explorer drifting toward it. Instead, the event horizon is better imagined as a point of no return written into the geometry of spacetime itself. It is a mathematical boundary with profoundly physical consequences. Outside that boundary, at least in principle, there are paths by which light can escape to the distant universe. Inside it, every possible future points inward. The distinction sounds abstract until one realizes that it determines the fate of every photon, every atom, every spacecraft, and every observer unfortunate enough to cross it. This leads to one of the most counterintuitive ideas in modern science. When astronomers say that one black hole is physically larger than another, they usually mean that its event horizon encloses a greater region of spacetime, not that there is more material occupying that volume. In fact, according to classical general relativity, nearly all of what we call the black hole is surprisingly empty. The mass is mathematically associated with an extremely small central region known as the singularity, although many physicists suspect that our current theories become incomplete before reaching such infinite densities. Quantum gravity, whatever form it ultimately takes, may replace the singularity with an entirely different structure. For now, however, the event horizon surrounds a vast region that cannot simply be thought of as a giant ball of matter. It is instead a domain where escape has become impossible because spacetime itself has been curved beyond a critical threshold. Then there is the shadow, perhaps the most visually captivating measurement of all. In 2019, the Event Horizon Telescope released humanity's first direct image of a black hole, revealing a bright ring surrounding a dark central region in the galaxy M87. Many people assumed they were looking directly at the event horizon itself. In reality, what appeared in the image was something slightly larger and even more fascinating. The dark area was the black hole's shadow, created because gravity bent and captured the paths of light traveling near the horizon. Imagine standing in a dense fog while a perfectly invisible sphere absorbs every beam of light passing too close. Even though the sphere itself cannot be seen, a dark silhouette naturally emerges because fewer photons reach your eyes from that direction. A black hole creates a similar effect on a cosmic scale, except the fog is replaced by superheated plasma glowing with extraordinary intensity. The shadow, therefore, is not identical to the event horizon. It is an optical consequence of gravity distorting the trajectories of light. Its diameter is typically several times larger than the horizon itself, making it easier for telescopes to detect across unimaginable distances. This distinction matters because future observations may allow astronomers to test Einstein's predictions with increasing precision. If a shadow were ever found to differ significantly from theoretical expectations, it could hint at new physics beyond general relativity. Such possibilities remain speculative today, but they illustrate why measuring black holes is not merely an exercise in cosmic bookkeeping. Every measurement becomes a test of our deepest understanding of gravity. Another subtle question sometimes arises. Could two black holes have identical masses yet appear different in size? Under the simplest conditions, the answer is essentially no, because the event horizon is determined primarily by mass and, to a lesser extent, by rotation and electric charge. Electric charge is expected to be negligible for astrophysical black holes because surrounding plasma quickly neutralizes it. Rotation, however, is a different story. Most real black holes almost certainly spin, some at astonishing fractions of the speed of light. Rotation slightly alters the shape of the event horizon, flattening it at the poles and changing the surrounding spacetime through an effect known as frame dragging. Rather than sitting quietly within the universe, spacetime itself begins to twist. The faster the spin, the more dramatic this twisting becomes. Yet even then, the overall size remains governed primarily by mass. Spin changes the details, not the fundamental scale. There is another reason astronomers prefer speaking in terms of mass. Diameter can be surprisingly difficult to define observationally. We cannot travel to a black hole carrying an enormous ruler. Even the largest event horizons occupy tiny angles on the sky because they are so far away. Instead, telescopes collect faint streams of light, X-rays, radio waves, and infrared radiation, piecing together indirect clues. Stellar orbits around Sagittarius A times at the center of our own Milky Way allowed astronomers to estimate its mass decades before its shadow was finally imaged. In distant quasars like TON 618, Scientists often rely on the motion of gas clouds illuminated by the brilliant accretion disk. Each technique carries uncertainties, assumptions, and statistical limits. This is why black hole masses are frequently reported with ranges rather than perfectly exact values. Science is rarely a collection of absolute numbers. It is a continuous process of narrowing uncertainty as better observations become available. Perhaps the deepest lesson hidden inside all these measurements is that black holes force us to abandon the ordinary idea that size belongs only to visible objects. A tree is large because we can see its trunk. A planet is large because we can touch its surface, at least in principle. A black hole is large because it reshapes the future of everything nearby. Its true dimensions are written not in rock or gas, but in the invisible architecture of space-time itself. The event horizon marks where possibility ends. The shadow reveals how light surrenders to gravity. The mass tells us how deeply reality has been curved. Together they describe something unlike anything else in nature. A cosmic object whose size is measured not simply by how much space it occupies, but by how profoundly it changes the meaning of space itself. And with that realization, an even more intriguing question quietly emerges from the darkness. If measuring a black hole is already so different from measuring every other object in the universe, what unimaginable conditions were required to build one whose mass reached tens of billions of suns in the first place? Long before anyone had ever heard the name TON 618, its light had already begun one of the longest journeys imaginable. It left its home when Earth looked profoundly different, when neither humans nor the civilizations that would one day build telescopes existed, when our species was still far beyond the horizon of evolutionary possibility. For more than 10 billion years, those photons crossed expanding space, slipping between forming galaxies, surviving encounters with clouds of intergalactic gas, quietly carrying a message from an era when the universe itself was much younger. By the time that ancient light finally reached modern observatories, it was no longer telling us only what TON 618 is. It was revealing what the universe looked like when much of cosmic history had yet to unfold. That alone makes TON 618 remarkable. But what truly transformed it into one of the most famous black holes ever studied was not simply its age or its extraordinary distance. It was the realization that hidden behind an object brighter than entire galaxies was one of the largest black holes humanity has ever measured. At first glance, this sounds almost contradictory. Black holes are supposed to be dark. They trap light rather than produce it. So why does TON 618 shine with such overwhelming brilliance that it can be detected across billions of light years? The answer reveals one of the most beautiful paradoxes in astrophysics. We do not actually see the black hole itself. We see everything that is desperately trying not to fall into it. Imagine an enormous whirlpool forming in the middle of a calm ocean. The center may appear almost invisible, yet the water rushing around it becomes increasingly violent as it spirals inward. Replace water with immense clouds of hydrogen, helium, dust, magnetic fields, and scattered stars. Replace the whirlpool with gravity so intense that space-time itself bends inward. As this material circles closer and closer to the event horizon, particles collide at astonishing speeds. Friction converts orbital energy into heat. Temperatures climb into the millions of degrees. The surrounding disk begins emitting radiation across nearly the entire electromagnetic spectrum, from radio waves to visible light to powerful X-rays. The black hole remains hidden, while its surroundings become one of the brightest beacons in the observable universe. This is why TON 618 belongs to a class of objects known as quasars. The word itself is a shortened form of quasi-stellar radio source, a name inherited from the early days of radio astronomy, when these mysterious objects looked almost like ordinary stars, despite releasing unimaginable amounts of energy. During the 1960s, astronomers gradually realized that quasars were not nearby stars at all. They were incredibly distant galactic nuclei powered by supermassive black holes consuming enormous quantities of matter. That discovery fundamentally changed our understanding of galaxies. Instead of being quiet collections of stars drifting through space, some galaxies possessed energetic hearts capable of outshining every star within them combined. TON 618 represents one of the most extreme examples ever found. Estimates of its mass place it above 60 billion solar masses, although, as with all measurements at such immense distances, uncertainties remain, and future observations could refine that value. Even so, the conclusion remains extraordinary. Whether the true figure ultimately proves somewhat lower or somewhat higher, TON 618 clearly belongs among the most massive black holes known through observational evidence. Reaching such a conclusion required remarkable ingenuity, because astronomers cannot simply place a black hole on a scale. Instead, they study the light emerging from gas orbiting close to the central engine. As this gas races around the black hole at thousands of kilometers per second, its spectral lines broaden in measurable ways. Using techniques developed over decades and combining observations with physical models describing the behavior of gas under powerful gravity, scientists can estimate both the velocity of the material and the gravitational influence required to produce those motions. Like detectives reconstructing an invisible event from scattered clues, they infer the mass of something they cannot observe directly. Naturally, these methods carry uncertainties. The geometry of the gas, the angle from which we observe the system, and assumptions built into the models all contribute to margins of error. This is why astronomers usually describe TON 618 as one of the largest known black holes, rather than declaring it the unquestioned champion forever. Science grows stronger through careful language, especially when dealing with objects lying billions of light-years away. Yet perhaps the most astonishing aspect of TON 618 is not simply how massive it became, but when it already existed. Because light travels at a finite speed, looking farther into space is equivalent to looking farther back in time. TON 618 appears to us as it was more than 10 billion years ago, when the universe was only a fraction of its present age. That simple fact quietly transforms the entire mystery. Somehow, before billions of additional years of cosmic evolution had unfolded, nature had already assembled a black hole whose mass rivaled tens of billions of suns. Every attempt to explain TON 618, therefore, becomes an attempt to understand one of the universe's fastest episodes of growth. Standard astrophysical models offer a plausible framework. Massive stars collapse into the first black holes. These early seeds gradually gain mass by pulling in gas from their surroundings. Galaxies merge repeatedly, delivering both fresh material and additional black holes that eventually coalesce. Over immense spans of time, a relatively ordinary black hole slowly transforms into a supermassive one. In broad outline, this picture explains much of what astronomers observe throughout the nearby universe. Yet objects like TON 618 encourage deeper questions because they appear so enormous so early. Could continuous growth alone truly build such giants within the available cosmic time? Many researchers believe the answer is yes under particularly favorable conditions, especially if sustained periods of rapid accretion occurred. Others investigate the possibility that some black holes began from unusually massive seeds produced by the direct collapse of gigantic primordial gas clouds rather than from individual stars. Still, other theoretical ideas explore whether dense star clusters, repeated mergers, or processes not yet fully understood may have accelerated early growth. None of these explanations has emerged as the definitive answer, and that uncertainty is precisely what makes TON 618 scientifically valuable. It is not merely a record holder, it is a challenge posed by the universe itself. There is another subtle feature that often escapes public attention. TON 618 is not simply feeding, it appears to be feeding with astonishing efficiency. The luminous accretion disk surrounding it converts gravitational energy into radiation far more effectively than nuclear fusion inside ordinary stars. This is one of the great surprises of black hole physics. Although black holes themselves emit essentially no light, Matter falling toward them can release a significant fraction of its rest mass as energy before disappearing beyond the event horizon. In terms of energy production, accretion onto a black hole can surpass the efficiency of the fusion reactions that power stars. The brightest object in the system is therefore not the black hole, but the doomed material making its final journey inward. This creates an image that feels almost poetic. The darkest object in existence becomes visible only because the universe briefly illuminates everything about to vanish forever. Yet the brilliance also hints at limitation. Black holes cannot consume matter arbitrarily fast. As gas heats and radiates, the escaping light pushes outward, opposing the inward pull of gravity. This balance, often described through the concept of the Eddington limit, suggests that sustained growth has natural constraints. If TON 618 accumulated tens of billions of solar masses while respecting those limits for most of its history, then it must have experienced extraordinarily long periods of abundant fuel or episodes of especially favorable conditions. Understanding precisely how that happened remains an active field of research. Perhaps future observations with increasingly powerful telescopes will reveal entire populations of similarly massive black holes hidden in the distant universe, showing that TON 618 is exceptional but not unique. Or perhaps it will remain one of the rare cosmic giants that formed under circumstances almost impossible to reproduce. Either outcome would teach us something profound about the history of galaxies. Standing before this realization, it becomes clear that TON 618 is much more than a colossal object occupying an unimaginably distant corner of space. It is a preserved chapter from the early universe, a gravitational archive written in light that has traveled for more than 10 billion years before reaching our eyes. Every photon arriving today left long before the solar system looked as it does now, carrying information across an expanding cosmos with astonishing patience. When astronomers point their instruments toward TON 618, they are not merely observing distance. They are witnessing deep time itself, compressed into a single point of extraordinary brightness. And once we accept that such a giant already existed when the universe was still comparatively young, an even more unsettling question naturally emerges. If one black hole could become this enormous so early in cosmic history, what would happen if an object of comparable size were somehow placed, not billions of light years away, but at the very center of our own solar system? Now imagine that the impossible has somehow become reality. Not a small stellar black hole left behind by an exploded star, not even the 4 million solar mass black hole that quietly resides at the center of our own Milky Way. But TON 618 itself has been placed at the exact center of the solar system. For a moment, forget the unimaginable engineering required to move such an object. Forget how galaxies would have to be rearranged to accomplish it. Treat it simply as a thought experiment, a careful exploration of gravity guided by the best physics we currently possess. It is a scenario that immediately sounds catastrophic. Yet the first surprise is that the disaster would not begin with an explosion. There would be no colossal blast racing outward through space, no wall of fire consuming the planets in dramatic succession. Black holes are not bombs. They do not radiate destruction merely because they exist. Their influence spreads through gravity, and gravity obeys remarkably consistent laws. That quiet beginning is precisely what makes this thought experiment so unsettling. The first consequence would occur before anything actually moved. The moment the sun disappeared and TON 618 occupied its place, the gravitational architecture of the solar system would become almost unrecognizable. The sun contains nearly all the mass in the solar system today, but TON 618 outweighs it by more than 60 billion times. Every orbit that has remained relatively stable for billions of years would suddenly become insignificant against this overwhelming gravitational field. Earth would no longer travel around a familiar star once every 365 days. Instead, it would find itself deep inside a gravitational landscape that had been completely rewritten. Yet even that statement hides something astonishing. Earth would not immediately cross the event horizon. Most people imagine a black hole as a tiny object with infinite gravity extending only from a small point. TON 618 forces us to abandon that image entirely. Its event horizon alone is estimated to span hundreds of billions of kilometers. Depending on the exact mass adopted, and whether one refers to the Schwarzschild diameter or related observational definitions, that invisible boundary would extend far beyond the orbit of Pluto and encompass a significant portion of what we currently call the outer solar system. In other words, if TON 618 occupied the Sun's position, nearly every familiar planet would already exist inside the region from which no light could ever escape. That realization changes the meaning of the question itself. We usually ask what would happen if a planet fell into a black hole. Here, the more accurate question becomes whether the solar system would even exist outside the black hole at all. The answer, according to current estimates, is almost certainly no. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto would all lie well within the enormous event horizon. Yet this creates another paradox that seems almost impossible at first. Crossing the event horizon of such an enormous black hole would not necessarily produce any immediate visual drama. Classical general relativity predicts that, for a sufficiently massive black hole, tidal forces at the horizon become surprisingly gentle. The difference in gravitational pull between your head and your feet, the force responsible for the famous stretching process called spaghettification, depends not only on mass, but also on the size of the horizon itself. As black holes become vastly larger, their horizons move farther from the central singularity, and the local tidal gradients decrease. If a spacecraft somehow drifted across the event horizon of TON 618, the crew might notice no sudden flash, no invisible wall, no instant tearing apart. Looking out the windows, the stars would still shine, although increasingly distorted by gravitational lensing. Instruments would continue operating normally. Clocks inside the spacecraft would continue ticking 1 second after another. The greatest transition in the known universe could, at least locally, feel almost disappointingly uneventful. That is one of Einstein's deepest insights. The event horizon is not a material surface. It is a boundary encoded into the geometry of space-time itself. Nothing physical announces your crossing. The tragedy lies not at the horizon, but in the impossibility of reversing course afterward. Every future path available to matter and light now leads deeper inward. From the astronaut's perspective, time continues normally. From the perspective of a distant observer, however, the story appears dramatically different. Signals leaving the spacecraft become increasingly redshifted. Light loses energy while climbing out of the immense gravitational well. The spacecraft seems to slow, fade, and approach the horizon ever more gradually, never quite appearing to cross it. Eventually, its image becomes so faint that it effectively disappears from view. This contrast between perspectives is not an illusion in the ordinary sense. Both descriptions emerge naturally from general relativity, illustrating that measurements of space and time depend profoundly upon the observer's frame of reference. Now picture the planets themselves. Earth would no longer experience familiar seasons because the sun would no longer exist. Sunlight, the source of nearly all biological energy on our planet, would vanish instantly if the sun itself were replaced. Within minutes, daylight would end forever. Surface temperatures would begin a relentless decline. Oceans would gradually freeze from the top downward, although geothermal heat, deep beneath Earth's crust, could preserve pockets of liquid water for extraordinarily long periods. The atmosphere would slowly condense as temperatures continued falling. Yet, compared with the overwhelming geometry of the black hole, these planetary catastrophes become almost secondary. The solar system would cease being a collection of planets orbiting a star, and instead become part of the interior region of one of the largest known gravitational structures in existence. Another extraordinary consequence concerns the sky itself. Inside such a gigantic gravitational environment, the appearance of the universe would transform in ways that challenge ordinary intuition. Light from distant galaxies would bend around the black hole, creating distorted arcs and rings through gravitational lensing. Some regions of the sky would appear compressed, others magnified. Stars, positioned behind the black hole, could produce multiple visible images, their light following entirely different paths, before eventually reaching an observer. Space would no longer behave as the flat, predictable stage on which celestial objects quietly move. Instead, the stage itself would curve, twist, and redirect every beam of light crossing it. Distances that appear straightforward in ordinary astronomy would lose their familiar meaning. Even the concept of looking in a particular direction becomes surprisingly subtle when space-time itself is no longer approximately flat. This leads naturally to an even deeper question. What actually exists inside the event horizon? Here, the confidence of physics becomes noticeably more cautious. General relativity predicts that every trajectory eventually approaches a central singularity, a region where the mathematical description yields infinite curvature and density. Most physicists interpret this not as proof that literal infinities exist in nature, but as evidence that the theory has reached the limits of its applicability. Quantum mechanics almost certainly becomes essential under such extreme conditions, yet a complete theory of quantum gravity remains one of the greatest unsolved problems in modern science. Some speculative models replace the singularity with finite quantum structures. Others propose entirely different internal geometries. A few ideas even suggest connections to baby universes or exotic space-time topologies, though none of these possibilities has gained broad observational confirmation. The honest scientific position is that we do not yet know what ultimately awaits beyond the region where current theories begin to fail. And perhaps that uncertainty is more fascinating than certainty itself. TON 618, therefore, becomes much more than an object holding a cosmic record. It becomes a tool for stretching our imagination, while simultaneously testing the boundaries of established physics. By asking what would happen if it occupied the center of our own solar system, we discover that the answer is not merely that everything would be destroyed. The deeper answer is that nearly every intuitive idea we possess about size, motion, distance, visibility, and even the flow of time would need to be rewritten. The solar system would no longer serve as a familiar neighborhood organized around a life-giving star. It would become a tiny geometric feature buried within one of the largest event horizons known to science. Yet even after imagining such an extraordinary transformation, another mystery quietly remains. If nature was somehow capable of building an object large enough to engulf an entire planetary system with its event horizon alone, what sequence of cosmic events could possibly have fed such a giant for billions of years without exhausting the available universe around it? By now, the scale of TON 618 has begun to feel almost unreal. A black hole whose event horizon could swallow much of our solar system sounds less like an astronomical object and more like an impossible thought experiment. Yet perhaps the most astonishing fact is not that it exists, but that the universe was somehow capable of building it at all. Every truly enormous structure in nature carries within it the memory of a long history. Mountain ranges preserve the slow collision of continents. Ancient forests record centuries of quiet growth. Galaxies reveal billions of years of gravity shaping stars into spirals and ellipses. Black holes are no different. A supermassive black hole is not born gigantic, it becomes gigantic. The real mystery, then, is not where TON 618 is located, but how nature managed to feed a single object until it accumulated more than 60 billion times the mass of our Sun without somehow running out of time, fuel, or stability. The simplest answer would seem obvious. It must have swallowed everything around it. Yet this intuitive picture turns out to be deeply misleading. Black holes do not consume the universe the way a vacuum cleaner pulls dust from a floor. Gravity has no preference for destruction. It merely shapes motion. Objects passing at sufficient distances continue orbiting normally. Entire galaxies can exist for billions of years with a supermassive black hole at their centers without being rapidly devoured. In fact, if black holes consumed matter as aggressively as popular culture often suggests, galaxies would likely look very different from what astronomers actually observe. Instead, the growth of a black hole is surprisingly inefficient, surprisingly delicate, and surprisingly dependent upon circumstances that must remain favorable for extraordinary lengths of time. Imagine pouring sand into a narrow funnel. If too much arrives too quickly, the flow jams and slows itself down. Something remarkably similar happens around black holes. Matter falling inward does not plunge directly through the event horizon. It first forms an accretion disk, an enormous rotating structure where gas particles collide, heat up, and radiate tremendous amounts of energy. That radiation does not simply escape into space without consequence. It pushes back against the incoming gas. As the disk grows brighter, its own light begins resisting the very process that created it. This natural balance is described through what astronomers call the Eddington limit, one of the most important ideas in understanding why black holes cannot grow arbitrarily fast. Although the limit is not an absolute wall and can, under certain circumstances, be exceeded temporarily, it represents a powerful regulatory mechanism built into the physics of accretion itself. The brighter the feeding process becomes, the more difficult it becomes to continue feeding at the same rate. Nature appears to have designed an elegant braking system. This immediately creates a fascinating puzzle. If black holes are constantly slowing their own growth through radiation pressure, how did giants like TON 618 reach such extraordinary masses within the age of the universe? One possibility is remarkably simple. They began growing very early and simply never experienced long periods of starvation. During the first few billion years after the Big Bang, galaxies contained abundant reservoirs of cold hydrogen gas. Star formation was vigorous. Galaxy collisions occurred far more frequently than they do today. Every collision stirred enormous clouds of gas toward galactic centers, potentially providing fresh fuel for central black holes. Rather than imagining TON 618 as a predator chasing isolated stars one by one, it may be more accurate to picture it as sitting at the center of a vast cosmic river whose currents delivered matter almost continuously for hundreds of millions of years. In that view, the black hole was not unusually hungry. It was unusually well supplied. Yet even this generous supply may not fully solve the problem. Modern observations, especially of extremely distant quasars, have revealed black holes reaching billions of solar masses when the universe itself was still remarkably young. In some cases, less than a billion years had passed since the Big Bang. Standard growth rates sometimes struggle to produce such enormous masses within that limited time. This has inspired one of the liveliest discussions in contemporary astrophysics. Perhaps the first black holes did not all begin as the remnants of ordinary massive stars. Instead, under rare conditions, gigantic primordial gas clouds may have collapsed almost directly into massive black hole seeds, containing tens of thousands or even hundreds of thousands of solar masses from the very beginning. Such direct collapse scenarios remain theoretical, and astronomers continue searching for observational evidence capable of confirming or rejecting them. Nevertheless, they offer an intriguing shortcut through one of cosmology's most difficult timing problems. Other researchers explore a different possibility. Perhaps the early universe itself behaved differently than we currently imagine. Dense star clusters may have produced repeated stellar collisions, assembling extremely massive stars that later collapsed into unusually heavy black holes. Others investigate episodes of super-Eddington accretion, periods during which black holes may have briefly consumed matter faster than classical limits would normally allow, especially if geometry or magnetic fields permitted radiation to escape preferentially in certain directions. Numerical simulations have shown that under specific circumstances, these episodes could significantly accelerate growth without violating fundamental physics. Whether such conditions occurred frequently enough to explain objects like TON 618 remains uncertain, but the possibility illustrates an important feature of science. The universe often achieves extraordinary outcomes not by breaking physical laws, but by exploiting every subtle opportunity those laws allow. Growth did not depend only on gas. Galaxies themselves were constantly evolving. Throughout cosmic history, galaxies collided, merged, and reorganized under gravity. When two galaxies merged, their central black holes began an intricate gravitational dance lasting millions of years before eventually spiraling together through the emission of gravitational waves. Each merger increased the total mass of the resulting black hole while simultaneously reshaping the host galaxy. In this sense, every giant black hole carries within it a family tree stretching back across countless generations of smaller ancestors. TON 618 is not simply one object. It is the accumulated history of innumerable stars, gas clouds, galaxies, and earlier black holes whose individual identities disappeared long ago within a single gravitational legacy. This perspective changes how we think about scale. We often imagine the largest black holes as isolated monsters. In reality, they may be better understood as archives of cosmic history. Their masses record billions of years of successful feeding, mergers, environmental conditions, and galactic evolution. Every additional solar mass tells part of a story extending far beyond the black hole itself. The surrounding galaxy, the neighboring galaxies, the large-scale structure of the universe, and even the expansion of space, all become participants in that story. Another remarkable insight emerges when we consider efficiency. Nuclear fusion inside stars converts only a small fraction of matter into usable energy. Accretion onto black holes, by contrast, can convert an even larger fraction of infalling mass into radiation before the material crosses the event horizon. This extraordinary efficiency explains why quasars, powered by supermassive black holes, can outshine trillions of stars, despite occupying comparatively tiny regions at galactic centers. Ironically, the process of feeding a black hole often produces some of the brightest objects in the observable universe. The darkest destination creates the brightest farewell. Yet all of these explanations still leave room for humility. Astronomy has entered a remarkable era in which increasingly powerful observatories continue revealing objects that challenge established expectations. The James Webb Space Telescope has already identified unexpectedly massive black holes in the early universe, prompting ongoing revisions to theoretical models. Future gravitational wave observatories may directly observe mergers involving intermediate and supermassive black holes across cosmic history. New radio telescopes may uncover previously hidden quasars buried behind dust. Every new generation of instruments expands the possibility that our current understanding represents only part of a much larger picture. It would therefore be premature to claim that the mystery has been solved completely. Instead, the evidence suggests that nature probably used several pathways simultaneously. Early massive seeds, sustained accretion, repeated galaxy mergers, favorable environments, and perhaps brief episodes of unusually rapid feeding may all have contributed in different proportions, depending on the history of each individual black hole. TON 618 may not owe its existence to one miraculous event, but to billions of years during which almost everything happened to go right. Seen from that perspective, its staggering mass becomes less an accident and more the cumulative result of extraordinary cosmic patience. The universe did not rush to create a giant. It spent billions of years assembling one cloud of gas, one galactic collision, one generation of stars, and one black hole merger at a time. And once that immense engine had finally reached such unimaginable proportions, something equally astonishing began to happen around it. The act of feeding the black hole no longer remained a quiet gravitational process. It transformed into one of the most luminous phenomena the cosmos has ever produced, where darkness itself became surrounded by light so brilliant that it could be seen across more than 10 billion years of cosmic history. If the universe possessed a single image capable of capturing both its greatest darkness and its greatest brilliance at the same moment, it would almost certainly be a quasar. From unimaginable distances, a quasar appears as a brilliant point of light, often shining so intensely that it overwhelms the combined glow of hundreds of billions of stars surrounding it. Yet hidden at its center is not a star, not a cluster of stars, and not an explosion. It is a black hole, the very object that, by definition, allows no light to escape once matter crosses its event horizon. At first, this sounds like an impossible contradiction. How can the darkest object in the universe become the engine behind one of its brightest phenomena? The answer reveals a deeper truth that stretches beyond black holes themselves. Nature often hides its greatest energies, not inside violent explosions, but within quiet processes that unfold patiently under the guidance of gravity. A quasar is not bright because the black hole shines. It is bright because gravity transforms falling matter into light with astonishing efficiency before that matter disappears forever. Imagine standing far above a vast whirlpool in a dark ocean during a perfectly still night. The center itself remains invisible, but around it stretches an enormous ring of glowing water, brighter than anything else on the sea. Every droplet racing inward collides with countless others. Motion becomes heat, heat becomes light. The closer the water approaches the center, the faster it moves, until the invisible drain is surrounded by a luminous spiral announcing its presence across the horizon. Replace water with hydrogen, helium, ionized plasma, magnetic fields, dust, and occasionally entire stars torn apart by gravity. Replace the ocean with the vacuum between stars. Replace the invisible drain with a supermassive black hole containing tens of billions of solar masses. The result is a quasar, a cosmic lighthouse, whose beacon can travel across more than 10 billion years of expanding space before finally reaching Earth. The remarkable thing is that almost everything we know about the largest black holes comes not from observing the darkness itself, but from studying this brilliant machinery surrounding it. Long before astronomers understood what quasars truly were, they appeared as one of the greatest mysteries in 20th century astronomy. During the late 1950s and early 1960s, radio telescopes detected extraordinarily powerful sources that looked almost like ordinary stars through optical telescopes. Their appearance was deceptively simple. Tiny points of light, no larger than stars, yet somehow producing far more energy than entire galaxies. At first, many astronomers hesitated to accept the enormous distances implied by their unusual spectra because the resulting luminosities seemed almost absurd. It was difficult to believe that nature could build something so energetic. Yet, as observations improved, the evidence became impossible to ignore. These objects truly lay billions of light-years away. Their brightness was not an illusion of proximity. They genuinely belonged among the most luminous, persistent objects in the observable universe. The solution arrived gradually through decades of theoretical work. At the centers of galaxies reside supermassive black holes. When abundant gas falls toward them, it cannot plunge directly inward because it possesses angular momentum. Instead, the gas spreads into an accretion disk, a rotating structure remarkably similar in principle to water circling a drain, although governed by far richer physics. Every orbit inside the disk becomes slightly faster than the one just beyond it. Neighboring layers rub against each other through turbulence, magnetic interactions, and microscopic collisions. This internal friction steadily converts orbital energy into thermal energy. Temperatures climb from thousands of degrees in the outer regions to millions of degrees closer to the center. The disk begins radiating across the electromagnetic spectrum with astonishing intensity. Visible light pours outward. Ultraviolet radiation floods surrounding space. X-rays emerge from the hottest inner regions where gravity reaches its greatest influence. The black hole itself remains silent, while everything approaching it briefly becomes one of the brightest phenomena in existence. One of the most surprising discoveries in modern astrophysics is that black holes are extraordinarily efficient engines, not because they produce energy directly, but because gravity extracts energy from infalling matter before it disappears. Inside the Sun, nuclear fusion converts only a small fraction of hydrogen's mass into energy, according to Einstein's famous equation, E equals mc squared. Around a rapidly spinning supermassive black hole, the conversion of gravitational potential energy into radiation can, under favorable conditions, exceed the efficiency of stellar fusion by a substantial margin. In other words, matter falling toward darkness can release more observable energy than matter undergoing fusion inside the brightest stars. This astonishing fact reverses ordinary intuition. We tend to associate light with creation and darkness with absence. Quasars remind us that the brightest farewell in the universe may occur immediately before matter is lost forever. Yet the brilliance of a quasar is not limited to the accretion disk alone. Above and below the disk, magnetic fields become twisted by the tremendous rotation of the system. Although many details remain active areas of research, theoretical models and observations strongly suggest that these magnetic structures can channel charged particles into narrow, highly energetic jets extending thousands or even millions of light-years beyond the host galaxy. These relativistic jets travel at speeds approaching that of light, carrying enormous amounts of energy into intergalactic space. They influence surrounding gas, regulate future star formation, and sometimes reshape entire galactic environments. In this sense, a supermassive black hole is not merely consuming matter, it is also participating in the long-term evolution of the galaxy that feeds it. The relationship is surprisingly balanced. The galaxy nourishes the black hole, while the black hole eventually alters the galaxy's future. This feedback process has become one of the central ideas in modern galaxy evolution. Without it, many computer simulations struggle to reproduce the galaxies astronomers actually observe today. The host galaxy and its central black hole appear to grow together over billions of years, influencing one another in subtle yet profound ways. The black hole is therefore not simply a parasite at the center of the galaxy. It is one participant in an intricate gravitational ecosystem spanning hundreds of thousands of light-years. There is another layer to this story that makes quasars particularly valuable to astronomers. Because they are so bright, they can be observed across extraordinary distances. Every quasar, therefore, functions as a beacon from the ancient universe. Its light passes through countless clouds of intergalactic hydrogen before reaching Earth. Those clouds absorb specific wavelengths, leaving delicate fingerprints within the quasar's spectrum. By studying these absorption lines, astronomers reconstruct the composition, temperature, motion, and chemical evolution of gas lying between galaxies billions of years ago. Remarkably, a quasar teaches us not only about the black hole creating it, but also about every region of space through which its light has traveled. It becomes simultaneously a laboratory for gravity and a flashlight illuminating the history of the cosmos itself. Even so, quasars do not shine forever. Their brilliance depends entirely on supply. Once the surrounding galaxy exhausts or disperses the gas capable of feeding the central black hole, the luminous accretion disk gradually fades. The galaxy may then appear quiet, its central black hole becoming almost invisible except through its gravitational influence. In this sense, the spectacular quasar phase may represent only one chapter in the life of a supermassive black hole rather than its permanent identity. TON 618 almost certainly did not spend its entire existence as an active quasar, nor will every giant black hole remain brilliantly illuminated indefinitely. Their brightest moments are temporary episodes within lives measured across billions of years. This realization adds an unexpected sense of calm to what initially appears overwhelming. The universe's greatest light factories are not eternal flames. They are brief periods of extraordinary activity surrounded by far longer ages of silence. Perhaps that balance between brilliance and stillness explains why quasars continue to fascinate scientists. They reveal that darkness is not the opposite of light, but, under the right circumstances, its greatest architect. The black hole contributes no photons of its own. Instead, gravity orchestrates a final transformation in which ordinary matter gives up an astonishing fraction of its energy before crossing an invisible boundary from which nothing returns. Every beam of light escaping a quasar is therefore a story interrupted at the last possible moment, a final message from matter standing at the edge of eternity. Yet as spectacular as quasars are, they introduce another unavoidable question. If we can only estimate the masses of these distant giants through indirect observations of their luminous surroundings, how confident can we truly be that TON 618 is among the largest black holes ever discovered? And could even greater monsters still be hiding beyond the limits of our current observations? After traveling through the immense scale of TON 618, it becomes almost irresistible to ask a simple question. Have we finally reached the top of the cosmic hierarchy, or is TON 618 merely the largest giant humanity happens to know today? At first, the answer seems as though it should be straightforward. Astronomers measure black holes, compare their masses, and rank them from smallest to largest. Yet the universe is rarely that cooperative. Unlike mountains on Earth, or planets within the solar system, black holes cannot be lined up beside one another for direct comparison. Every estimate depends upon light that has traveled across billions of years, upon physical models describing gas that can never be touched, and upon observations made from one tiny planet orbiting an ordinary star inside one ordinary galaxy. The deeper astronomers investigate this question, the more they discover that the largest known black hole is not a permanent title. It is a snapshot taken from humanity's current position within an unfinished exploration. TON 618 remains one of the strongest and most widely cited candidates for the largest black hole whose mass has been estimated with substantial observational support, typically placed at more than 60 billion solar masses. That description is important because science deliberately distinguishes between known, measured, and possible. There are other candidates with estimated masses reaching tens of billions of solar masses, including central black holes associated with exceptionally massive galaxies and luminous quasars. Some estimates even approach or exceed 100 billion solar masses. However, those measurements often carry significantly larger uncertainties or depend upon assumptions that remain actively discussed within the astronomical community. The farther we look into the universe, the less direct our measurements become. Rather than diminishing the science, this uncertainty reflects the honesty with which astronomy treats its own limitations. One of the reasons comparisons become so difficult is that no single technique exists for weighing every supermassive black hole. Nearby black holes can sometimes be measured by watching stars orbit their centers over many years. Every complete orbit acts almost like the hand of a cosmic clock, revealing the hidden mass through gravity's influence. This approach produced remarkably accurate measurements for Sagittarius A, the black hole at the center of the Milky Way. But objects like TON 618 lie far beyond the reach of individual stellar observations. Their host galaxies appear as tiny points, even through the most powerful telescopes. Instead, astronomers must infer mass indirectly, by studying the rapidly moving gas within the broad line region surrounding the active nucleus. Spectral lines become broadened because different clouds move toward and away from Earth at tremendous speeds. Combined with estimates of distance and luminosity, these observations allow researchers to calculate an approximate gravitational mass. The method is powerful, but it is not perfect. Small changes in assumptions about geometry, viewing angle, or gas dynamics can produce noticeable differences in the final result. This explains why two published studies may occasionally report somewhat different masses for the same black hole without either being fundamentally incorrect. Scientific measurement is not simply about obtaining a number. It is about estimating both the number and the uncertainty surrounding it. Another challenge arises from selection bias, an idea that quietly shapes almost every astronomical survey. The observable universe is unimaginably vast, yet humanity has examined only a tiny fraction of it in sufficient detail. We naturally discover the brightest quasars first, because they stand out across enormous distances. Quiet supermassive black holes, even if equally massive, are far more difficult to detect because they produce little radiation. A dormant giant hidden within a distant galaxy could remain almost invisible unless its gravitational influence happened to reveal itself through unusually favorable circumstances. This means the absence of evidence cannot automatically be interpreted as evidence of absence. There may well be larger black holes than TON 618 scattered across the observable universe that simply have not yet announced themselves in ways our current instruments can recognize. At the same time, caution works in both directions. Extremely large mass estimates occasionally attract attention because they are extraordinary, but extraordinary claims demand particularly careful examination. Over the past several decades, some initially reported record-breaking black holes have later received revised mass estimates after improved observations or more sophisticated models became available. This continual refinement is one of the strengths of astronomy, rather than a weakness. As telescopes improve, uncertainties shrink, assumptions are tested more rigorously, and measurements gradually converge toward more reliable values. In many ways, the history of black hole research is a history of increasingly precise humility. Every generation believes it has reached the limits of measurement, only for the next generation to discover new techniques that reveal additional complexity. There is another fascinating reason why the largest black hole may never hold its title forever. The universe itself is still evolving. Galaxies continue to merge. Black holes continue to accrete matter, although generally at much slower rates than during the peak quasar era billions of years ago. Every major galactic collision has the potential, over immense spans of time, to produce an even larger central black hole. The record book is therefore not frozen. Cosmic history continues writing new chapters, even if the timescales involved extend far beyond the lifetime of humanity. Somewhere in the distant future, a black hole larger than TON 618 could emerge naturally through processes already understood within standard astrophysics. Whether intelligent observers will exist to witness such an event is an entirely different question. Curiously, theoretical physics also places subtle constraints upon how rapidly these giants can grow. Every black hole depends upon a supply of matter. Every galaxy contains only finite resources. Radiation from the accretion process limits sustained feeding rates through mechanisms related to the Eddington limit. Galaxy mergers become less common as the universe expands and structures drift farther apart. None of these factors creates an absolute upper boundary, but together they suggest that nature does not produce arbitrarily massive black holes with equal ease. Growth becomes increasingly difficult as environments become depleted and cosmic evolution progresses. The largest known black holes may therefore represent the products of extraordinarily favorable histories rather than ordinary outcomes repeated throughout the universe. Some theoretical studies have explored whether black holes with masses approaching hundreds of billions of solar masses, or even beyond, could exist under exceptional circumstances. Current physics does not categorically forbid such objects, provided sufficient matter and sufficient time are available. Yet observational evidence for black holes of that scale remains limited. Some reported candidates rely upon indirect methods that continue to be debated, while others await confirmation through future observations. It is therefore more scientifically accurate to describe these possibilities as open questions rather than established discoveries. This distinction matters because astronomy advances by separating what has been measured, what has been inferred, and what remains hypothetical. The excitement comes not from pretending certainty where none exists, but from recognizing how much remains to be learned. Future observatories may transform this discussion entirely. The next generation of extremely large ground-based telescopes will resolve galactic centers with unprecedented detail. Space observatories, operating across infrared, X-ray, and radio wavelengths, will extend humanity's ability to identify distant quasars hidden behind dust. Gravitational wave detectors planned for future decades may even observe mergers involving supermassive black holes directly, allowing entirely new methods of estimating their masses. Every technological leap expands the volume of the observable universe we can explore with confidence. It would therefore be surprising if today's catalogue ultimately proved complete. History suggests the opposite. Every time astronomy acquires a sharper eye, the universe reveals structures larger, older, or stranger than previously imagined. There is also a philosophical lesson quietly hidden within this search. The desire to identify the largest black hole resembles humanity's fascination with the tallest mountain, the deepest ocean trench, or the oldest fossil. Records help organize curiosity, but they rarely represent the deepest scientific question. Whether TON 618 remains the largest known black hole for another decade, or is eventually surpassed by a newly discovered giant, matters less than understanding the physical processes capable of producing either one. The record holder may change. The underlying physics is the true destination. In that sense, TON 618 has already achieved something more important than keeping its place at the top of a list. It has forced astrophysicists to refine growth models, improve measurement techniques, reconsider early cosmic evolution, and ask better questions about the relationship between galaxies and the enormous gravitational engines hidden within them. Perhaps the greatest contribution of a cosmic giant is not its size, but the questions it compels us to ask. And among those questions, one rises quietly above the rest. Even if the universe has already produced black holes larger than TON 618 somewhere beyond the reach of our current telescopes, is there a fundamental limit imposed by physics itself, or could gravity, given enough matter and enough time, continue building objects whose event horizons stretch across distances almost impossible for the human mind to imagine? After discovering that TON 618 may not necessarily represent the final champion, an even deeper question begins to emerge from the silence of the cosmos. Suppose the universe continues evolving for another 100 billion years. Suppose galaxies continue merging, black holes continue feeding, and gravity never stops doing what gravity has always done. Could black holes simply keep growing forever, or does nature eventually impose a limit? At first glance, the answer seems almost obvious. If a black hole becomes larger every time it gains mass, then why should there be any upper boundary at all? Add another star, add another galaxy, wait another billion years, repeat the process indefinitely. Yet this apparently simple logic overlooks something fundamental. Black holes do not exist outside the universe. They grow within it, and the universe itself is governed by finite resources, finite time, and physical processes that gradually change as cosmic history unfolds. To understand how large a black hole can truly become, we must stop thinking about black holes in isolation and instead ask a much broader question. What limits the universe itself? One of the first surprises comes from a fact that almost sounds impossible. As a black hole grows larger, its average density actually decreases. This seems completely backwards. We often imagine larger black holes as becoming increasingly compressed, increasingly dense, and increasingly extreme. That intuition is accurate for the tiny central region described by classical general relativity, but it is not true for the black hole as a whole. The event horizon expands in direct proportion to mass, while the enclosed volume increases much faster. If one calculates the average density enclosed within the event horizon of an extremely massive black hole, the result becomes astonishingly low. For the largest known supermassive black holes, the average density can fall below that of water. Push the calculation further toward hypothetical black holes hundreds or thousands of times larger still, and the average density continues dropping. In principle, a sufficiently enormous black hole could possess an average density comparable to Earth's atmosphere, or even less. This does not mean black holes become weak or harmless. Their gravitational influence remains immense because gravity depends upon total mass and space-time curvature, not simply average density. Nevertheless, the result quietly overturns one of our oldest mental pictures. The largest black holes are not gigantic balls of impossibly compressed matter filling every part of their interiors. They are vast regions of space-time bounded by an event horizon whose scale grows faster than most people instinctively imagine. This realization leads naturally to another question. If density becomes less restrictive as black holes grow, perhaps nothing prevents gravity from assembling truly unimaginable giants. Classical general relativity itself offers surprisingly little resistance. Mathematically, Einstein's equations do not contain a built-in maximum mass for an astrophysical black hole. Given enough matter collected within the appropriate radius, an event horizon forms regardless of whether the object contains 10 solar masses or 10 trillion. In that narrow mathematical sense, relativity does not appear to prohibit arbitrarily massive black holes. Yet mathematics alone does not build objects. The universe must still provide the raw material, and here reality begins introducing practical limits that may prove far more important than purely theoretical ones. Every supermassive black hole feeds from its surroundings. Gas falls inward. Stars occasionally wander too close. Entire galaxies merge over billions of years, but none of these reservoirs is infinite. Galaxies gradually consume much of their cold gas through star formation. Violent quasar activity can heat or expel additional gas, reducing future fuel supplies. Galaxy mergers become less frequent as cosmic expansion carries many large structures farther apart. The universe itself is aging. In its youth, collisions occurred often and fresh material flowed abundantly into galactic centers. Today, those opportunities have become less common. Far into the future, they may become extraordinarily rare. The expansion of the universe, therefore, acts as a subtle but persistent limitation upon black hole growth. Gravity tries to gather matter together, while cosmic expansion increasingly separates distant structures from one another. Neither force wins completely. Instead, they define the environment within which black holes evolve. Another important limitation arises from the feeding process itself. Even if unlimited gas somehow surrounded a black hole, accretion cannot proceed infinitely fast. As matter spirals inward, friction heats the gas until radiation pours outward with tremendous intensity. That escaping light exerts pressure against newly arriving material. This self-regulating behavior, described approximately through the Eddington limit, means that sustained periods of extremely rapid growth become increasingly difficult. Under special circumstances, black holes may briefly exceed this limit, particularly if inflowing gas possesses unusual geometry, or if radiation escapes preferentially along certain directions. Numerical simulations suggest such episodes are physically plausible and may have played an important role in the early universe. Even so, these phases are generally expected to be temporary rather than permanent. Nature appears willing to accelerate growth, but not indefinitely. Some theoretical studies have attempted to estimate realistic upper masses for black holes formed through ordinary cosmic evolution. Although no universally accepted maximum exists, many models suggest that black holes, significantly exceeding several 100 billion solar masses, would require exceptionally favorable histories involving repeated galaxy mergers, sustained accretion, and unusually rich environments over enormous spans of time. Objects approaching 1 trillion solar masses remain speculative. Current observations provide no confirmed examples, but neither do they absolutely rule them out. The absence of evidence simply reflects the extraordinary difficulty of observing such rare systems across the immense volume of the universe. There is another subtle factor that often receives less attention. Galaxies themselves may struggle to remain efficient suppliers once their central black holes become sufficiently massive. Powerful radiation, energetic jets, and enormous outflows generated during active quasar phases can heat surrounding gas or drive it away from the galactic nucleus. In effect, a rapidly growing black hole may begin disrupting the very environment upon which its future growth depends. This feedback mechanism appears to regulate both galaxy evolution and black hole evolution simultaneously. The larger the black hole becomes, the more capable it becomes of limiting its own food supply. Growth, therefore, contains the seeds of its own slowdown. One might describe it as a conversation between gravity and energy that continues across billions of years. Gravity pulls matter inward. Radiation pushes outward. Neither completely dominates. Their balance gradually shapes the largest structures in the universe. Yet perhaps the most intriguing possibility lies beyond ordinary astrophysical growth altogether. Some speculative cosmological models ask whether black holes substantially larger than anything produced inside galaxies could arise through entirely different mechanisms. Primordial black holes, if they exist, formed not from collapsing stars, but from density fluctuations in the extremely early universe. Most proposed primordial black holes would be much smaller than supermassive ones, but certain theoretical scenarios have explored whether unusual conditions might allow exceptionally massive primordial seeds. At present, observational evidence for such ideas remains inconclusive. Likewise, proposals involving exotic dark matter interactions, modified gravity, or entirely new physics occasionally appear within the scientific literature. These ideas are valuable because they test the boundaries of current theory, but none has yet achieved broad observational support. They remain possibilities rather than accepted explanations. There is also a question that sounds almost philosophical. Could the observable universe itself contain enough matter to create a black hole vastly larger than every galaxy combined? In principle, if sufficient mass were somehow compressed within the appropriate radius, general relativity predicts that an event horizon would form. But this thought experiment quickly collides with cosmology. The universe is expanding, matter is distributed across enormous distances, and no known process gathers all cosmic material into a single gravitational object on observable scales. Rather than asking whether physics allows such a black hole mathematically, astronomers ask whether the universe possesses any realistic mechanism capable of assembling it. So far, no convincing mechanism has emerged. The distinction between mathematical possibility and astrophysical plausibility becomes essential. Nature often chooses only a tiny fraction of what equations technically permit. Looking even farther ahead, black holes themselves are not eternal according to current theoretical understanding. Stephen Hawking showed that quantum effects near the event horizon imply an extraordinarily slow loss of energy through what is now called Hawking radiation. For stellar and supermassive black holes, this process is unimaginably slow, vastly exceeding the current age of the universe. A giant such as Ton, 618, would survive for periods so immense that every star now shining in the cosmos would have long since faded before evaporation became significant. Yet the existence of Hawking radiation carries profound conceptual weight. Even the largest black hole does not represent an eternal endpoint. Given enough time, far more than the human mind comfortably comprehends it too, would gradually disappear. The greatest gravitational structures ever assembled would eventually surrender to quantum physics, one infinitesimal particle at a time. This extraordinary conclusion reminds us that limits arise not only from size but also from time. Perhaps that is the deepest answer to the question of how large a black hole can become. Physics does not currently provide a simple numerical ceiling comparable to the speed of light. Instead, it offers a network of interacting constraints: the amount of available matter, the efficiency of accretion, the evolution of galaxies, the expansion of the universe, feedback from radiation, and the immense passage of cosmic time itself. Together, they suggest that nature is capable of building objects far beyond ordinary imagination, yet not without cost, patience, and favorable circumstances extending across billions of years. Ton, 618, therefore may represent neither an absolute limit nor merely one giant among infinitely larger neighbors. It may instead occupy a region near the practical frontier where the universe begins running out of opportunities rather than running out of physical laws. And if that frontier truly exists, then perhaps the most meaningful way to appreciate its scale is no longer through equations or theoretical limits alone, but through the one measuring tool that has accompanied us since the beginning of this journey, light itself, whose finite speed transforms unimaginable distances into something the human mind can finally begin to picture. Numbers eventually reach a point where they stop communicating anything meaningful. 60 billion solar masses sounds extraordinary, but after hearing enough zeros, the human mind quietly gives up. Hundreds of billions of kilometers become little more than symbols on a page. This is why astronomers often rely on a different language when trying to understand truly immense structures. Rather than measuring them in kilometers or miles, they measure them in time. More specifically, they ask a beautifully simple question. How long would light, the fastest traveler the universe allows, need to cross from one side to the other? Suddenly, an object is no longer just large. It becomes something capable of delaying even light itself. And that transformation changes the way we imagine the largest black holes forever. Light occupies a unique place in physics because nothing carrying information can outrun it. Every distance in astronomy eventually becomes a story about travel time. Sunlight takes a little more than 8 minutes to reach Earth. The glow from Jupiter arrives after roughly 40 minutes, depending on the planet's positions. Neptune lies about 4 light hours away. Even Voyager 1, the most distant spacecraft humanity has ever launched, remains less than a single light day from Earth, despite traveling for nearly half a century. These comparisons already stretch intuition, yet they still belong to our familiar cosmic neighborhood. The moment we begin speaking about the largest black holes, even these scales become surprisingly small. Imagine standing impossibly far away from TON 618 with an unobstructed view of its immense gravitational silhouette. You decide to perform the simplest experiment conceivable. At one edge of the black hole's event horizon, a beam of light begins traveling perfectly straight toward the opposite edge. Nothing distracts it. Nothing scatters it. It moves at the maximum speed permitted anywhere in the universe. Yet instead of completing its journey in seconds or minutes, the light continues traveling hour after hour, day after day, depending upon the exact mass assumed for TON 618 and the precise definition of the boundary being measured. Crossing the diameter of the event horizon alone requires several days. If, instead, we refer to the apparent shadow produced by gravitational lensing, the dark silhouette actually targeted by projects like the Event Horizon Telescope, the journey becomes even longer because the shadow appears substantially larger than the horizon itself. Suddenly, the phrase "the size of a black hole" acquires a completely different emotional weight. We are no longer discussing an invisible point in space. We are discussing a region so enormous that light itself experiences it as a significant voyage. This way of thinking reveals something subtle about astronomy. Time often becomes a more intuitive ruler than distance. Imagine hearing that a valley stretches 50 kilometers across. Now imagine hearing that it would take a person an entire day to walk from one side to the other. The second description feels immediately more tangible because it translates geometry into experience. Astronomers do something remarkably similar when they speak of light minutes, light hours, light days, or light years. Instead of asking how large something is, they ask how long reality's fastest messenger would need to cross it. In doing so, they quietly replace abstract mathematics with motion. There is another reason this perspective matters. The shadow of a black hole is not simply the event horizon viewed from far away. Earlier, we explored the distinction between the horizon and the shadow, but here that difference becomes physically important. The event horizon marks the boundary beyond which escape is impossible. The shadow, however, is created because gravity bends the trajectories of photons traveling near the black hole. Some photons narrowly escape. Others become trapped in unstable orbits before eventually falling inward or escaping in different directions. Many disappear completely. The result is a dark region appearing larger than the event horizon itself, surrounded by an intensely luminous ring where bent light accumulates. In other words, the shadow is gravity made visible through geometry rather than through matter. It is not the black hole itself we observe. It is space-time revealing its own curvature. This distinction was spectacularly confirmed in 2019 when the Event Horizon Telescope released humanity's first image of the supermassive black hole in the galaxy, M87. What appeared as a glowing ring surrounding a dark interior was not a photograph of a solid object. It was an image of light, struggling through one of the strongest gravitational fields in the universe. Every photon reaching Earth's telescopes had followed a path dictated by Einstein's equations. The black hole itself remained invisible, while gravity painted its outline across the sky. That achievement represented far more than a technological milestone. It transformed general relativity from elegant mathematics into something humanity could literally see. Now imagine performing that same observation around a black hole like TON 618. Its shadow would dwarf those surrounding ordinary stellar black holes, not because gravity becomes fundamentally different, but because the entire region over which light is dramatically redirected expands to extraordinary dimensions. A photon passing nearby no longer experiences merely a brief deflection. It enters a vast gravitational landscape extending across billions of kilometers. Every path becomes part of a larger conversation between motion and curvature. The black hole does not reach outward to capture light. Instead, space-time quietly guides light toward its own fate. There is something profoundly calming about this image despite its immense scale. Gravity does not shout, it whispers with absolute consistency. Thinking in light time also reveals an unexpected comparison. Our Sun appears unimaginably large from Earth, yet sunlight crosses its diameter in only a few seconds. Earth's diameter requires a fraction of a second. Jupiter, the largest planet in the solar system, measures only a few light seconds across. Even the Sun's entire planetary system out to Neptune spans merely several light hours. By contrast, the shadow surrounding a giant like TON 618 occupies a scale measured not in seconds or hours but in days. A traveler, made entirely of light, would spend nearly a week simply traversing the darkness surrounding a single object. That comparison accomplishes something no numerical table ever could. It allows the imagination to breathe. The black hole is no longer merely large. It possesses duration. It contains enough spatial extent that even the universe's fastest traveler cannot ignore the passage of time while crossing it. Yet there is another subtle consequence hidden inside this perspective. Because light requires time to move across these immense regions, changes occurring near the black hole cannot appear instantaneous even to nearby observers. Different portions of the accretion disk communicate through radiation subject to finite travel times. Variations in brightness propagate outward. Echoes of energetic flares may illuminate distant gas clouds only after measurable delays. Astronomers have developed sophisticated techniques known as reverberation mapping, precisely because these time lags contain valuable information about the sizes of structures surrounding active black holes. Remarkably, the finite speed of light becomes a measuring tape. Instead of physically traveling to a quasar, scientists watch its brightness fluctuate and measure how long different regions take to respond. The delays reveal distances hidden inside objects billions of light-years away. Once again, time quietly becomes geometry. Perhaps this is one of the deepest lessons offered by the largest black holes. Human intuition evolved in a world where light appears instantaneous. We turn on a lamp, and a room fills immediately with illumination. Yet the universe operates differently. Nothing communicates infinitely fast. Every beam of light carries with it a history measured in travel time. When those journeys extend from seconds to days merely to cross a single object's gravitational silhouette, our ordinary sense of scale begins dissolving into something richer. Distances become stories unfolding at the speed of causality itself. Even silence acquires measurable length. There is also a philosophical elegance hiding here. We often imagine darkness as the absence of information, yet the shadow of a black hole is one of the most information-rich structures in modern astrophysics. Its size tests Einstein's theory. Its shape reflects the black hole's mass and spin. The surrounding ring reveals the behavior of hot plasma and magnetic fields. The delays experienced by light encode distances impossible to measure directly. The darkest region in the universe, therefore, becomes one of the most powerful laboratories for understanding gravity. What appears empty is, in reality, filled with geometry. What appears silent is speaking continuously through the paths taken by photons. Looking at TON 618 through this lens, the question, how big is it, evolves into something more profound. Its greatness is not merely that its shadow stretches across distances requiring days for light to cross. Its greatness lies in the realization that time itself becomes the ruler by which its existence is understood. We no longer measure the black hole only with kilometers or solar masses. We measure it using the patience demanded of light. And once we begin viewing the universe that way, another extraordinary possibility quietly comes into focus. If a single black hole can preserve within its size the history of light traveling across days, perhaps its true significance extends far beyond its own event horizon. Perhaps every giant black hole is also preserving the story of the galaxy that built it, making the largest black holes not merely records of gravitational growth, but living archives of the entire history of cosmic evolution surrounding them. By the time we arrive at the largest black holes in the universe, it becomes clear that we are no longer studying individual objects. We are reading biographies written across billions of years. A black hole like TON 618 is so massive that it cannot be understood as a single destination reached by gravity alone. Its extraordinary size is the accumulated result of countless events that unfolded long before the light we observe today ever began its journey toward Earth. Every star that was born, every cloud of gas that drifted through a young galaxy, every collision between neighboring galaxies, every generation of supernovae, enriching the surrounding environment with heavier elements. All of these seemingly separate stories eventually became chapters in the history of one enormous gravitational engine. In that sense, asking how large a black hole has become is almost the same as asking what kind of life its galaxy has lived. The two histories are woven together so tightly that modern astronomy increasingly treats them as different expressions of the same cosmic evolution. This realization did not emerge immediately. For much of the 20th century, astronomers largely viewed supermassive black holes as fascinating but isolated objects hiding inside galactic centers. Galaxies were thought to evolve primarily through star formation, gravity, and collisions, while black holes simply occupied the middle like passive observers. Over the past few decades, however, observations have steadily transformed that picture. One of the most influential discoveries was the unexpected relationship between the mass of a galaxy's central black hole and the properties of the galaxy's central bulge of stars. Although there is considerable scatter and ongoing refinement, galaxies with larger stellar bulges generally host more massive central black holes. This empirical relationship, often called the M-sigma relation, was surprising because the black hole itself occupies only an extraordinarily tiny fraction of the galaxy's total volume. Somehow, structures separated by tens of thousands of light-years appeared to know about each other's growth. That correlation suggested something profound. The black hole and the galaxy were not evolving independently, they were growing together. Imagine walking through the rings of an ancient tree. Each ring records a season of growth, years of drought, years of abundance, changes in climate that occurred long before anyone was present to observe them. Astronomers read galaxies in much the same way. Spiral arms preserve episodes of star formation. Globular clusters preserve the earliest stellar populations. Streams of stars stretching through galactic halos reveal long-forgotten mergers with smaller galaxies. The central black hole records another part of that history. Every increase in its mass required matter to reach the galactic center. Every feeding episode depended upon the large-scale evolution of the galaxy itself. In this sense, the black hole becomes less like an isolated monster and more like the deepest archive within the entire system. Consider what must happen for a galaxy to nourish a black hole over billions of years. Gas cannot simply appear at the center. It must first cool within enormous molecular clouds, lose angular momentum through gravitational interactions, migrate inward, survive intense radiation, and continue spiraling toward the nucleus. Despite turbulence, magnetic fields, stellar winds, and countless competing processes. During galactic mergers, the situation becomes even more dramatic. As two galaxies pass through one another, tidal forces distort their shapes, compress gas clouds, and trigger bursts of star formation. Vast streams of material begin flowing toward the newly forming galactic center. There, enormous quantities of fresh fuel become available for the central black holes. Eventually, those black holes themselves may spiral together and merge, producing an even larger gravitational engine. Every major collision, therefore, changes not only the appearance of a galaxy, but also the future of its central black hole. The larger the black hole becomes, the more likely it is that its host galaxy has experienced a long and complicated history of mergers rather than remaining quietly isolated. Yet the relationship works in both directions. The black hole does not simply receive matter from the galaxy. It also shapes the galaxy's future. When enough gas falls into the accretion disk, tremendous amounts of energy are released. Radiation floods the surrounding environment. Powerful winds race outward. Relativistic jets, driven by magnetic fields near the rotating black hole, can extend far beyond the visible boundaries of the host galaxy. Rather than remaining trapped at the center, enormous quantities of energy are carried outward into interstellar and even intergalactic space. This process, known broadly as active galactic nucleus feedback, has become one of the central ingredients in modern galaxy formation models. Without it, computer simulations often produce galaxies that continue forming stars far more rapidly than observations suggest. The black hole therefore behaves not only as a consumer of matter, but also as a regulator. By heating surrounding gas or pushing portions of it away, it may reduce future star formation and gradually limit its own supply of fresh material. Growth and restraint become parts of the same cycle. There is something quietly elegant about this balance. The larger the black hole becomes, the greater its ability to prevent itself from growing indefinitely. Another remarkable insight emerges when astronomers compare galaxies across cosmic time. Looking deeper into space means looking farther into the past, because light requires time to travel. Observations reveal that the universe experienced an era often called cosmic noon, roughly 10 to 11 billion years ago, when star formation and quasar activity both reached extraordinary levels. This was a universe rich in cold gas, frequent mergers, and rapidly evolving galaxies. It was also the period during which many supermassive black holes accumulated much of their mass. As the universe expanded, galaxies gradually consumed or expelled much of their available gas. Merger rates declined. Quasar activity became less common. The brightest growth phase slowly faded. The enormous black holes we observe today are therefore fossils from an earlier and more dynamic universe. Their masses preserve evidence of conditions that no longer dominate the present-day cosmos. In this way, a giant black hole becomes a time capsule. It remembers an era that the surrounding stars alone cannot fully describe. There is another layer to this story that makes the largest black holes particularly valuable. Massive galaxies occupy special locations within the cosmic web, the immense network of filaments composed of dark matter, gas, and galaxies stretching across the observable universe. The richest clusters of galaxies formed where these filaments intersected, creating environments favorable for repeated mergers over billions of years. A black hole like TON 618 almost certainly did not grow inside an ordinary galactic neighborhood. It likely benefited from an exceptionally favorable location within the large-scale structure of the universe itself. Its history, therefore, extends beyond its host galaxy. It reflects the evolution of an entire region of the cosmos. Gravity operates on every scale simultaneously, from the motion of gas clouds around the event horizon to the migration of galaxies through clusters hundreds of millions of light-years across. Each scale influences the next. The black hole becomes the final collector of histories written across vastly different sizes and timescales. Yet despite these increasingly sophisticated models, important questions remain unanswered. Recent observations with the James Webb Space Telescope have identified unexpectedly massive black holes in galaxies that appear surprisingly young. In some cases, the apparent ratio between black hole mass and stellar mass seems difficult to reconcile with simple coevolution scenarios. Do black holes sometimes grow first, helping to shape the galaxies around them? Or do galaxies still lead the process, with observations temporarily biased by selection effects or incomplete measurements? Current evidence has not settled this debate. Many astronomers suspect that several evolutionary pathways exist simultaneously, depending upon environment, merger history, gas supply, and cosmic epoch. Rather than following one universal script, galaxies and black holes may engage in a variety of evolutionary conversations whose outcomes differ across the universe. That possibility adds depth rather than confusion. Nature often proves richer than our earliest models anticipate. Perhaps the most beautiful consequence of all this research is that it changes the meaning of the largest black holes. At first glance, they seem to represent the triumph of gravity over everything else. Yet the deeper we look, the more they resemble records of cooperation rather than domination. They exist because stars were born, because galaxies collided, because gas cooled efficiently, because dark matter assembled large structures, because gravity patiently organized matter over billions of years, and because the expanding universe created just the right sequence of opportunities before gradually closing many of those windows forever. Every enormous black hole is therefore much more than an endpoint. It is the cumulative memory of an entire cosmic neighborhood written into a single gravitational object. Seen this way, TON 618 ceases to be merely one of the largest black holes known. It becomes one of the most complete historical documents the universe has ever preserved. And if its mass truly records billions of years of galactic evolution, then the greatest mysteries surrounding black holes may no longer concern their size alone, but the earliest moments of cosmic history that first set this extraordinary chain of events into motion, leaving behind clues that astronomers are only now beginning to uncover. By now, it may feel as though the story has reached its natural conclusion. We have followed the largest known black holes, from their unimaginable masses to their immense event horizons, from the brilliant quasars surrounding them to the galaxies that patiently built them across billions of years. Yet astronomy has a remarkable habit of becoming more uncertain precisely when it becomes most fascinating. The closer we move toward the frontier of knowledge, the fewer firm answers we possess. The universe does not reward curiosity with neat endings. Instead, it reveals deeper questions hiding beneath every apparent solution. Perhaps that is the greatest surprise of all. The largest black holes are not merely the biggest objects gravity has assembled. They are also the places where some of modern physics becomes least complete. Every observation answers one question, while quietly creating several more. In that sense, the darkness surrounding these giants is not simply the absence of light. It is the boundary of our current understanding. One mystery stands above nearly all the others. Where did the very first supermassive black holes come from? It is tempting to imagine a simple evolutionary ladder. A massive star dies. A stellar black hole forms. It gradually consumes gas, merges with neighboring black holes, and after enough time becomes a supermassive giant. This sequence certainly explains many aspects of black hole growth, but the earliest universe complicates the picture. Observations now reveal quasars powered by black holes, containing billions of solar masses, less than 1 billion years after the Big Bang. On cosmic timescales, that is astonishingly early. Even under favorable conditions, continuously feeding a small stellar remnant until it reaches billions of solar masses, within such a limited interval, proves challenging for many standard growth models. Nature appears to have moved with remarkable speed. The question is whether our understanding of that speed remains incomplete, or whether the universe began with far larger black hole seeds than we once imagined. One proposed solution is known as direct collapse. Rather than beginning with ordinary stars, enormous clouds of pristine hydrogen and helium may, under rare circumstances, have collapsed almost directly into massive black hole seeds, containing tens of thousands or perhaps hundreds of thousands of solar masses. Such objects would possess a tremendous head start compared with ordinary stellar remnants. Computer simulations suggest that special environments in the early universe could suppress fragmentation, preventing the gas from breaking into many individual stars and allowing a much larger structure to collapse as a whole. It is an elegant idea because it addresses the timing problem naturally. Yet elegance alone is not evidence. Astronomers continue searching for observational signatures capable of confirming whether direct collapse black holes truly existed. Some promising candidates have been proposed, but no universally accepted example has yet settled the debate. Another possibility turns attention away from the seeds themselves and toward the feeding process. Perhaps the earliest black holes simply grew much faster than we usually assume. Classical calculations often rely upon the Eddington limit as a long-term average constraint, but the early universe may not have behaved so quietly. Dense gas clouds, chaotic mergers, and unusually favorable accretion geometries might have allowed repeated episodes of super-Eddington growth, during which black holes briefly accumulated matter faster than traditional limits would suggest. Numerical simulations have demonstrated that such episodes are physically plausible under certain conditions. The unresolved question is whether they occurred frequently enough and lasted long enough to explain the earliest known quasars. Here again, theory offers possibilities, while observation continues gathering evidence. There is another mystery that reaches beyond astrophysics into the foundations of physics itself. According to classical general relativity, matter falling through the event horizon ultimately approaches a singularity, a region where density and space-time curvature formally become infinite. Most physicists do not interpret this mathematical infinity as the literal description of nature. Instead, infinities are generally viewed as signals that an existing theory has reached the limits of its validity. Quantum mechanics governs the microscopic world with extraordinary success. General relativity governs gravity on cosmic scales with equally remarkable precision. Yet inside black holes, these two pillars of modern physics are expected to collide. No complete theory successfully unites them under the extreme conditions found near singularities. Whatever ultimately replaces the classical singularity almost certainly belongs to a deeper theory of quantum gravity that humanity has not yet discovered. This means the interiors of black holes remain hidden not only behind event horizons, but also behind the boundaries of present-day theoretical physics. Some speculative ideas propose that singularities never truly form. Quantum effects may halt complete collapse before infinite density is reached, replacing the classical picture with an exotic quantum state. Other models explore gravitational condensates, Planck-scale structures, or entirely new geometries hidden beneath the event horizon. A few hypotheses suggest that black holes could connect to baby universes, wormhole-like configurations, or regions disconnected from our observable cosmos. These ideas are intellectually stimulating because they extend existing mathematics into unexplored territory. But it is essential to distinguish possibility from evidence. At present, none of these proposals has achieved broad observational confirmation. They remain valuable scientific hypotheses rather than established descriptions of reality. The greatest strength of science lies precisely in that distinction. Another unresolved question concerns the relationship between black holes and dark matter. Dark matter outweighs ordinary matter throughout the universe, shaping galaxies through its gravitational influence while remaining invisible to every telescope operating across the electromagnetic spectrum. Does dark matter contribute significantly to black hole growth? Could dense concentrations of dark matter have accelerated the formation of the earliest supermassive black holes? Most current evidence suggests that ordinary gas dominates the rapid accretion responsible for luminous quasars, yet dark matter still governs the large-scale gravitational framework within which galaxies assemble. Whether more direct interactions exist remains uncertain. Future observations and improved particle physics experiments may eventually clarify this relationship, but for now the connection remains largely indirect. The expanding universe introduces another puzzle. As dark energy gradually drives galaxies farther apart, opportunities for future mergers decrease. Does this mean the era of giant black hole growth is already fading? Many astronomers believe so. The brightest quasar epoch occurred billions of years ago when gas was abundant and galaxies collided frequently. Today, most massive black holes appear comparatively quiet. They remain enormous, but many no longer feed at the extraordinary rates that once illuminated the early universe. If this picture is correct, then humanity exists during a transitional era. We arrived late enough to observe the fossil giants left behind by cosmic history, yet early enough that their ancient light still reaches our telescopes. That coincidence carries a certain quiet beauty. We are witnessing the aftermath of the universe's most energetic period, while enough evidence still survives to reconstruct what happened. New observatories promise to reshape these mysteries over the coming decades. The James Webb Space Telescope has already revealed surprisingly mature galaxies and unexpectedly massive black holes at very early cosmic times, prompting astronomers to reconsider long-standing assumptions. Future extremely large telescopes on Earth will resolve distant galactic centers with unprecedented detail. Planned gravitational wave observatories such as LISA are expected to detect mergers involving massive black holes across vast cosmic distances, allowing researchers to watch these giants grow through entirely new forms of observation. For the first time, astronomy will not rely solely on light. It will also listen to the vibrations of space-time itself. Every improvement in technology expands the possibility that questions appearing mysterious today may become measurable tomorrow. Yet experience suggests that every answer will uncover still deeper questions beyond it. Perhaps the most profound mystery is not hidden inside any single black hole, but within the remarkable effectiveness of the laws governing them. Einstein developed general relativity without observing quasars, event horizons, or gravitational waves. More than a century later, his equations continue describing phenomena across scales he could scarcely have imagined. Why should mathematics conceived on one small planet describe the behavior of objects billions of light-years away with such astonishing accuracy? Is that simply the nature of physical law, or does it hint at an even deeper level of order waiting to be understood? Science cannot yet answer that question, but neither can it ignore it. Every successful prediction quietly deepens the mystery of why the universe remains so consistently intelligible. In the end, the largest black holes teach us something unexpected. Their greatest value does not lie in breaking records or dominating lists of extreme objects. Their greatest value lies in exposing the edges of human knowledge with extraordinary clarity. They reveal where our theories remain strong, where they begin to weaken, and where entirely new ideas may eventually emerge. TON 618 and other cosmic giants are therefore not merely destinations for curiosity. They are signposts pointing toward the next generation of discoveries. And perhaps that is the most fitting role for the darkest objects in existence. Rather than concealing the truth forever, they illuminate the path toward questions humanity has only just begun to ask, leaving one final thought lingering in the quiet vastness of space. If the greatest black holes ultimately reveal more about the universe than about themselves, then perhaps the true answer to how big the largest black hole really is cannot be separated from the story of the cosmos that created it in the first place. When we first asked how big the largest black hole in the universe is, the question sounded wonderfully simple. It seemed to promise a single number, a definitive record, perhaps one astonishing comparison capable of satisfying our curiosity. But somewhere along this journey, the question quietly transformed. The answer was never going to fit inside a number alone. Numbers can describe mass, diameter, or the time light needs to cross an event horizon, yet none of them fully captures what a giant black hole actually represents. A black hole like TON 618 is not remarkable merely because it may contain more than 60 billion times the mass of the Sunday. It is remarkable because every one of those billions of solar masses records a history stretching across nearly the entire lifetime of the universe. To measure such an object is not simply to measure gravity. It is to measure time, evolution, patience, and the extraordinary ability of nature to build complexity over billions of years without ever hurrying. That realization changes the meaning of scale itself. Throughout human history, we have instinctively associated greatness with physical size. Mountains appear powerful because they rise above the landscape. Oceans inspire awe because they stretch beyond the horizon. Planets seem immense because they dwarf our own world. Black holes invite us to abandon that familiar intuition. Their true size is not expressed only through distance but through influence. They reshape the paths of stars. They regulate the evolution of galaxies. They bend the trajectories of light itself. They preserve within their masses the memory of countless generations of stars that formed, lived, and disappeared long before Earth existed. A giant black hole is therefore less like a mountain and more like a historical archive written into the geometry of space-time. Every additional solar mass tells a story that no ordinary object could ever preserve. Perhaps this is why the largest black holes continue to fascinate astronomers, despite remaining almost completely invisible. We rarely observe the black hole directly. Instead, we reconstruct its existence through consequences. We watch stars orbit empty space. We measure gas accelerating to extraordinary velocities. We observe brilliant quasars illuminating the darkness surrounding invisible horizons. We detect gravitational waves carrying news of ancient mergers across billions of light years. Piece by piece, evidence accumulates until an object that cannot be seen begins to acquire remarkable clarity. There is something profoundly satisfying about this method. It reminds us that science often advances not by looking directly at the answer, but by carefully understanding everything the answer leaves behind. In many ways, the largest black holes teach us as much about scientific reasoning as they do about gravity itself. They reward patience over certainty and evidence over intuition. One of the most beautiful lessons hidden within this exploration is that simplicity often returns after immense complexity. We began by discussing extraordinary numbers, tens of billions of solar masses, event horizons spanning days in light travel time, galaxies colliding over billions of years. Yet beneath all of these details lies a remarkably simple principle. Gravity never stops working. It acts patiently, consistently, and without interruption. Given enough matter and enough time, it organizes the universe into structures of astonishing scale. Stars become galaxies. Galaxies merge into larger systems. Black holes grow alongside them. Nothing in this process requires urgency. The cosmos accomplishes its greatest achievements through persistence rather than speed. There is something quietly comforting about that idea. The universe builds its masterpieces one orbit, one cloud of gas, one collision, one generation of stars at a time. Yet even after everything we have explored, honesty requires acknowledging what remains uncertain. TON 618 is among the most massive black holes known through current observations, but future discoveries may reveal even larger examples. Improved telescopes may refine its estimated mass. New techniques may uncover dormant giants hidden within distant galaxies whose light has not yet been interpreted correctly. The James Webb Space Telescope has already demonstrated that the early universe continues to surprise us with unexpectedly mature galaxies and enormous black holes. Future gravitational wave observatories will almost certainly reveal mergers that no optical telescope could ever witness. Every advance in technology expands the boundaries of what humanity is capable of measuring. The largest known black hole today may not remain the largest known black hole tomorrow. That possibility does not weaken the story. It strengthens it. Science is not diminished when it discovers something larger. It is fulfilled. There is another subtle realization waiting beneath the surface of this entire journey. We often describe black holes as places where information disappears, where light cannot escape, where certainty comes to an end. Yet from the perspective of astronomy, the opposite is almost true. Supermassive black holes have become some of our richest sources of information about the history of galaxies, the behavior of gravity, the evolution of the early universe, and perhaps one day, even the long-sought union between quantum mechanics and general relativity. Their darkness has become unexpectedly generous. By refusing to reveal themselves directly, they have forced humanity to invent new telescopes, develop more sophisticated mathematics, refine theories of gravity, and build instruments capable of detecting the faint vibrations of space-time itself. The darkness has not hidden knowledge. It has inspired it. That may be the deepest paradox of all. We also arrive at a humbling perspective on humanity's place within the cosmos. The photons carrying information about Ton 618 began their journey billions of years before Earth acquired its present appearance. Long before mammals evolved, before continents assumed their modern shapes, before the first human looked upward and wondered what the stars might be, those photons were already traveling across expanding space. They continued their silent voyage, while civilizations rose and disappeared, while languages were invented, while mathematics slowly matured into a tool capable of describing gravity itself. Only now, after more than 10 billion years, have a tiny fraction of those photons entered telescopes built by a civilization existing for only the briefest instant of cosmic history. That perspective does not make humanity seem insignificant. Instead, it makes our curiosity extraordinary. The universe owed us no explanation. Yet, through observation, mathematics, and patient questioning, we have learned to reconstruct the existence of objects so distant that their light predates our species entirely. Perhaps intelligence is remarkable precisely because it allows a small corner of the universe to become aware of the rest. Looking ahead, the story of giant black holes is far from complete. Every generation inherits better instruments than the one before it. The coming decades will almost certainly reveal black holes hidden inside galaxies too distant, too dusty, or too faint for present observations. Artificial intelligence will help identify subtle patterns buried within enormous astronomical surveys. Space-based gravitational wave observatories will listen to mergers unfolding across billions of light-years. Radio interferometers stretching across continents will sharpen humanity's view of event horizons. The next record-breaking discovery may already exist in data that have been collected but not yet fully understood. History repeatedly reminds us that the universe tends to exceed expectations whenever our ability to observe it improves. There is little reason to believe that trend has ended. And so we return, at last, to the question that began this entire journey. How big is the largest black hole in the universe? The most honest answer is that the largest confirmed examples known today possess masses measured in tens of billions of suns and event horizons so vast that light itself requires days to cross them. But that answer, accurate though it may be, captures only the surface of the truth. The deeper answer is that the largest black hole is not defined only by its mass, its diameter, or its shadow. It is defined by everything those measurements represent. It is the cumulative history of galaxies feeding a gravitational heart across billions of years. It is the visible consequence of invisible space-time curved to extraordinary extremes. It is a laboratory where Einstein's equations continue to withstand astonishing tests while simultaneously revealing where new physics may eventually emerge. It is a reminder that even the darkest places in existence can become the brightest sources of understanding. And perhaps, as you let your thoughts drift quietly through the immense silence of the cosmos one final time, the most remarkable realization is not that the universe contains objects large enough to humble every scale we have ever imagined. It is that the human mind, despite existing on a small world orbiting an ordinary star, has learned to follow ancient light across billions of years, decode the language of gravity, and ask questions vast enough to reach those distant giants in the first place. In the end, the greatest achievement may not belong to the largest black hole at all. It may belong to curiosity itself, a force with no event horizon, no measurable boundary, and perhaps no true limit. Thank you for spending this quiet journey through the universe with Sleepy Space. If you enjoyed exploring the cosmos together, please subscribe, Leave a like, and I'll see you in our next peaceful adventure among the stars.